All right, so we're going to look at another easy problem next. It's LeetCode 3346, minimum positive sum subarray. And yeah, I like easy problems because they allow you to practice the interview process and your systematic approach without getting too distracted by trying to solve the problem. Because if the problem is easier, you can focus more on the process than on the problem solution. And as you ramp up and get better, you start to pick medium problems and maybe sometimes a hard problem where you then have to do a lot more thinking to solve the problem. But at that time, you already know exactly, how to systematically approach a problem. And this framework really gives you, well, something you can practice. So that's why I'm a big advocate of trying to solve problems that are easy, just to solve the interview, just to practice the interview process. If you're only after solving coding challenges, then you might want to use a completely different approach. But that's not what we are interested in. So as usual, let's start with reading through the problem description and the constraints and then the examples before we start to come up with a solution. So again, minimum positive sum subarray. You are given an integer array nums and two integers L and R. Your task is to find the minimum sum of a subarray, those size is between L and R inclusive, and those sum is greater than 0. Okay, nums L and R. Why are they called L and R? So it's like a left and right pointer, typically. But yeah, I don't like the naming of those variables. Anyway, let's continue. Return the minimum sum of such subarray. If no such subarray exists, return -1. The subarray is a contiguous non-empty sequence of elements within the array. So something like this would be a subarray, but if we skip any elements, then that's not a subarray more. I believe then it's a subsequence. So subarray versus subsequence, important to understand the difference. And here we're dealing with subarrays. Nice. So we need to find a subarray that has a sum that is greater than 0, and we have some constraints on the length of the subarray. And yes, and we need to find the minimum sum subarray. The constraints are, okay, so there's at least one element in our original array. Interesting, the length of the subarray is guaranteed to also be smaller than the actual length of the array that we're given. So that's an edge case we don't have to take care of. And then some information about the range of values in a subarray. Although I don't think it really matters. But what is important, I think, is we deal with negative numbers as well. And we only want to look at subarrays that have a sum of their elements that is greater than 0. So, okay, so we can have subarrays where the sum is possibly smaller than 0, and then we can consider it for the minimum sum subarray. Nice. Let's just go through the examples here. So here we're giving nums, 4 numbers, and we're looking for a subarray of length 2 to 3 with a minimum sum larger than 0. So what are the subarrays of length 2? I guess this would be 1, and here the sum is 3 minus 2 equals 1. So that's actually what the output is. Okay, so maybe this is already the minimum sum subarray we were looking for. But let's go through the other ones. So -2 and 1, there's another subarray of length 2, but here the sum is -1, so we can't consider this subarray. This is the third subarray of length 3 in this array. Sum of elements is 5, so it's definitely larger than 1. And now all the subarrays of length 3, I think they're 2, this one and that one. And in both cases, the value is larger than 1, right? So this would be 2 would be some of the elements, and this one would be 3. So the minimum is 1. Yes. And yeah, that is exactly what we just went through. Those are the examples. Nice. So we actually we had a negative value in our optimal subarray, but the sum of the elements was larger than 0. Okay, cool. Second example, again, we're looking for, well, we got 4 elements in our nums array. We're looking for a subarray of length 2 to 3. So let's go through them. So this would be 0, the sum of the elements. This would be -1. This would be -2. Now length 3 subarrays. So this would be -3, and that one would be -2. So none of them were larger than 0. And if no such subarray exists, we should return -1, which is why we're returning -1 here. Cool. Okay, last example. When we're giving more than 2 examples, I mean, I think we already understand the problem, but it's good practice to go through all of the examples when you're giving examples. It reduces the chance of you making any rash judgments or errors because you didn't pay attention. So let's just go through the last example as well. We're looking for a subarray of length 2 to 4. Excuse me. And because the numbers are sorted here, we can already discard this subarray. We can discard that one. We can discard that one. We can also discard that one, and we can discard the subarray of length 4. So the smallest one is likely going to be this one. And yeah, that's the correct answer. Now, there are no guarantees about how the elements are ordered in our array. In this example, they are ordered, but we can't really infer anything from that. If we knew that all of these arrays would be array elements would be ordered, even with negative numbers, it would be quite easy for us to find the optimal subarray. We would pick the minimum length, and we just have to find the point where the sum of the minimum length subarray just goes above 0. And yeah, you could probably use and this is a tangent, right? You could probably use a binary search to find the optimal position in your long subarray of where the sum is actually just above 0. And so you would have, if the length is n, you would have well, you need log n steps to identify the best position, and each step requires you to take k steps, where k is the difference between L and R. So it will be k log n effort and runtime, and 0 space, which is really nice. Anyways, that's another cool problem actually. So if you want, try to solve that on your own and see if I was right. But back to this one. So you're right. So when I look at this problem, so I'm immediately thinking that, well, we need to iterate over all of the elements, and then we have to take care of the different sizes of these subarrays. Now, I wonder if it's possible to come up with an O of n solution. And there's probably some genius out there who comes up with that solution, but I'm not that genius. But what I can see is that, we could iterate through all of the required subarray sizes, and just for each of the size, we iterate through our nums array to compute all of the size k windows. So these two, that two, that two. And so it's kind of a sliding window approach. And it's pretty much what we've been doing while we went through these examples. We could just put that into code, right? That would be the first approach. And that's probably what I would do right away. So I would, tell the interviewer that I want to implement exactly that, because I don't see yet a more efficient solution. And I would say, there are 2 ways, I suppose, of how to handle these sliding windows. One is by actually using a data structure to store the elements that are currently in the sliding window. For example, if we have, if we're looking for subarrays of size 2 in this example, our sliding window might contain the 3 and the 2. Then when we move to the next position where the 1 is, we have to pop out the 3. So we could use like a deck, like a LIFO, a FIFO, first in, first out data structure that allows us to add and pop elements from it in constant time. That might give us the simplest code where we don't have to juggle around with indices. But I think we can then optimize it to a solution where we actually have a constant space requirement, where we compute, well, where we just keep track of the current subarray sum. And we know at which position we are. And when we move to the next position, we know that we have to subtract the value of the array at that position. So when you are at the coding interview, depending on your form, and by the time you're prepared, you have a pretty good feeling of what you can do and what you can't do. The best approach is always to hammer out a solution that just works. Just give them something, be quick, don't make mistakes, and then iterate on that to improve it. You know, that's much better than trying to come up with an optimal solution and then just mess up because of some off by one error and not get it working, and you get tangled up in a mess of debugging, which is well, it will just kill your interview performance. So yeah, let's just keep it simple. Let's implement the first thing that we see that will work. We can already give a runtime complexity analysis for this. So we will iterate n times, let's say n times n over the array time and O of m space, where n is the length of our array. And m is equal to the difference between L and R. And I guess +1, right? But that doesn't, I mean, that's a constant, but anyways, yeah. So that, I think, is the runtime and the space complexity of the first solution that I'm going to implement now. And we have to keep track of the minimum sum. And I like to sometimes just call it result. It just makes it easier to know what that thing is. You could also call it the minimum sum if you wanted to. I like result just by convenience. And yeah, and how do we initialize it? Well, it could be that we can't find a solution, and in that case we should return the -1. And so we need to be able to identify when we didn't find a solution, but we also want to update our result with the minimum of whatever our current window sum is and result. So I think I'm just going to use a marker value, just infinity. So if we do a minimum of result with something else, it will become that something else. But in the end, when result is still infinity, we know we need to return 1, right? So if result is infinity, we just have to return -1. Otherwise, we return result. That's pretty much what we do. Cool. So now the next thing is to loop over the window sizes. So we have an outer loop over the window size and an inner loop over, well, over the elements of the array. So for window size in range L and R plus 1, because it said here explicitly the size is L and R inclusive. And then we have to keep track of the current window sum, window sum, and we initialize the window sum with 0. Okay, and now we need to iterate over all of the elements in the array. And well, we also need to take care of the data structure to store all these elements. And one thing we can do is we can use the FIFO that I talked about earlier in Python. You have the deck. And I don't think you have to import it in LeetCode, but in other environments, you might have to just import it, so that's available. So what we do here now is we have the window, and that will contain all of the values of nums that are currently inside the window. And that is going to be our deck. Right. So now we're going to iterate over the elements in nums. For n in nums. And what we'll do is we will do window.append our value n, and we'll also update our window sum. So plus equals n. And let me just check real quick. The constraint of the window size was 1 or more. So it's guaranteed that we will never have an empty window. Cool. So now what we have to do is we have to check the length of the window. If the length of the window is equal to our window size, that means this window sum is eligible for to be the minimum sub-array sum. Otherwise it's not. But of course we have to check if the window sum is larger than 0, then it can be considered, right? So then we say the result is the minimum of the current result and the current window sum. And now, since we already know that the window size is full, and we've now checked if the current sum is eligible and potentially updated the minimum, we can already pop out the first inserted element from that window. So when we step into the next iteration of for loop, we can add a value again, and then we have the full window size again. And in Python, you use pop left. There's a pop, which pops it from the right side. There's a pop left that pops it from the left side. And you can see the deck basically as an array, but it has the pop and it has the pop left. Not poop, pop, right? And all of these operations are O of 1, which it's really nice. If you have a regular array, then popping from the left side is actually an O of n operation, n in the length of the number of elements in it. So that's why we're using the deck here to keep the runtime of the pop left to O of 1. Cool. And yeah, that should be pretty much it. Now I've been talking a lot, probably much more than I would in an interview. So I'm just going to speed it up a little bit and hit the run button. And normally you would do like a step-by-step mental debugging through your code. Is everything correctly? Oh, and I should probably do it because we're updating our window sum here, but we're not decreasing it here. So we actually have to decrease it here as well. So yeah, taking shortcuts is not a good idea. Cool. I think that's it. I'm just going to run it. See what happens. Ooh, nice. And let's submit it. There you go. So that is accepted and that works. And so now, can we optimize this further? Yes, we can. I think we can, at least we can optimize it to O of 1 space. So let's try to do that. And to do that, we will get rid of our deck. So we won't need this. And but we have to now identify the value which we will subtract in this case, where we would normally do the pop left. So for that, I would use 2 pointers. So what I would do is, I would say n is, well, we have a left pointer and a right pointer. I would say the leading pointer is this one, right, in range lang nums. And we also have a left pointer that points to the last element in our window. And that is the right one, but minus, what do we subtract? Well, the window size, right? Window, I wish I could type window size. And when we increase the window sum, we just point it to the right, to nums where right is pointing. And when we decrease it, what we do is we just use the left pointer. That's pretty much what we do. And instead of checking if the length of the window is the size, what we do is we check if the left pointer is larger or equal to 0. So, and because the left will point to negative values until the full window is basically looking at the area. So in the beginning, if we have a window size of 2, we're looking at the right will be pointing to 0, and the left will be pointing to -2. And then we move 1 forward, and then the right is pointing to 1, and the left is pointing to, it should be pointing to 0 instead of -2. So we probably have to correct this and add 1 here. Yeah, we need to add 1 here. So yes. So that is, I think, how we can do that. So we correct our space complexity to O of 1. We still have the 2 loops, right? And this is a slightly more efficient solution, but it's also a little bit more difficult to get right. So that's why I wouldn't implement this as my first implementation. But yeah. So that concludes that. I hope you enjoyed that video. Thanks for watching.